I guess since most people are here, let's get started. So it's a great pleasure to have Professor Kathryn Johnston visiting us from Columbia University. And Kathryn got her PhD in 1996 from UC Santa Cruz. And then she spent some time at the IAS in Princeton, after which she was a junior faculty at Wesleyan University in Connecticut. After that, she moved to her present position at Columbia University, which she's held for more than a decade now. She's recently started as a group leader at the Center for Computational Astrophysics, CCA New York. So she's visiting us from a joint appointment at both these places. And today she's going to talk about Welcome to the Milky Way.
Great, thanks, Hamza. Okay, thanks very much. Thanks for the invitation. It's nice to be here. Welcome to the Milky Way. So this talk is really my perspective on some recent results from the Gaia satellite, the last year and a half or so. Really exciting results from the Gaia satellite. And I admit to this being very much a review talk rather than being really focused on my own work. And partly I feel some responsibility to do that sort of talk, having thought about this work for the last couple of decades. So I wanted to share some of the excitement with you who may or may not, I know some of you are, but may or may not be part of the Milky Way community working on Gaia. And I should also be clear, I said the Gaia satellite, but really this work is built on the last couple of decades of surveys of millions and now billions of stars in the Milky Way that have allowed us to have this fantastic view of our home galaxy and to know it very well. So it's not just the Gaia satellite itself. So I'm a galactic dynamicist and I work on the Milky Way. So the background of my work is thinking about Binney and Tremaine and stellar populations. And you put those two things together and you can start to ask questions about the Milky Way. But it's always good to think about the bigger context as well. And the context for this, if we can put it into three buckets. One would be the work we do here can go in the bucket of near-field cosmology, where we think about the distribution and therefore the nature of dark matter, a rather big question in itself. Secondly, we have a view of galaxy formation. You can think of the Milky Way. I mean, you can think of it as just one galaxy. I'm actually much more interested in what it means for galaxy formation more generally. So you can think of it as a giant laboratory for studying galaxy formation. Along that line as well, the other exciting thing is to make the connection between the Milky Way and the early universe, meaning there are stars in the Milky Way that we can observe today that were born in the early universe. So in some ways, this is a window on the early universe, which is entirely complementary in both senses of the word, of the two different spellings of the word, to what you might see by looking at high redshift. And in some ways, you can see things here using individual stars in the Milky Way that you cannot see in situ at high redshift. So these are the exciting things I think about when I say I study the Milky Way. I'm actually not that interested in the galaxy itself. Shh, that sounds terrible, but I'm more interested in these bigger questions. So I also wanted to mention a couple of things I'm not going to talk about because this is more of a review talk about Gaia results. I wanted to give you a flavor of some of the things I work on. So with David Hendel, I work on low surface brightness features around galaxies more generally. What might we do when we've got millions of galaxies from LSST, where we can look at very low surface brightness features around them? And this is building from what we understand from the Milky Way. A second area of work that I'm not going to talk about is there's a really fun direction that I've been taking with a few graduate students in the last few years, and we have a great collaboration going on talking about fundamental dynamics and ways of observing very fundamental dynamical processes and looking at observations of stars in our galaxy and beyond. And lastly, there is this other section on dynamics, a very different application of different dynamics to try and understand social interactions in our field and how that may or may not allow us to build constructive workplaces. And that's a topic that I'm talking about tomorrow lunchtime if you'd like to come along. It'll be partly talk, and hopefully there will be time for discussion as well. So back to Gaia, and I want you to, let's stop for a minute and just think about Gaia in the most exciting way. In other words, we'll pretend I'm giving a public review talk, in which case I would say, okay, the Gaia satellite can measure positions extremely well on the sky, which sounds extremely boring. But for example, if you took a tennis ball and you put it on the moon, Gaia measures positions well enough that you'd be able to tell one side of the tennis ball from the other, which is really quite remarkable. Another example would be, here I am walking at walking pace in Toronto. Well, if I was doing that around the next nearest star beyond the sun, so Proxima Centauri, then you would be able to see, Gaia would be able to detect me walking, maybe a little faster than this, but not a lot, right? So Gaia is this incredible machine for detecting positions and also motions in the galaxy. And as astronomers, we know that positions, with positional detection, we can also get distances via parallax, right? So if you take this position accuracy and this mission goes over time, you can get to distance and motion via proper motion, distance via parallax, proper motion, just from motion on the sky. And in other words, for the first time, we're measuring the full phase-space distribution function of stars in our galaxy, or indeed of any galaxy in the universe. And we can do this for a significant fraction, not the whole galaxy. By the end of the mission, it'll be about a quarter of our galaxy in terms of number of stars. And the second equality is where I want to go here, because of course, if you have a phase-space distribution function for a galaxy, this is a 6-dimensional phase-space distribution function. And the beautiful thing about dynamics is, under some assumptions of equilibria, you can actually reduce that to describing this instead of positions and velocities for every star in the galaxy. We could describe it in terms of populations of orbits. So this J is labeling the orbits, in this case, in terms of actions, and it's a more compact way of describing our distribution function. So what we're going to do in this talk is I'm going to remind you of Binney and Tremaine. That's going to take us about 10 or 15 minutes. And we're going to do Binney and Tremaine in about 10 and 15 minutes to remind ourselves of the flavor of what's going on in there and get a nice intuitive feel for this sort of description of the galaxy. And then we're going to talk about interactions in the galaxy as well. And after that, we're going to take a look at the Gaia data. And mostly that's not my own work. It'll be looking at the data that's come out from Gaia and some of the beautiful results. And then we're going to summarize and ask, how can we put these things together to learn about the galaxy and use it as a laboratory on the universe? So if we start with galactic dynamics, we'll start by talking about where I left off, this equilibria question. Wait a second, I think we've missed a slide. I feel like we've missed a slide. No, I want to double check where this slide is coming up. Sorry, I was doing so well. Where is this? Okay, I'm just going to look ahead, because this is a neat slide. We need to see. Okay, we'll just carry on. We'll worry about that slide later. Maybe it'll show up, and I've just forgotten where it is. Okay, galactic dynamics, equilibria. Let's start by talking about orbits. Because that's, I was saying we go from position and velocity and we're going to go to orbits. So let's remind ourselves of how we're going to describe orbits. And I'm going to be showing you, because we have this beautiful map of the galaxy, I'm going to be showing you some 6D phase-space projections of that. So if we start from 2D position in the galaxy, in the disk, most of those orbits are circular or near circular. If you blow this up a bit, you can actually see this is the red orbit is something that's almost exactly circular. And then you've got a blue orbit and a green orbit, if we just blow up part of it, where they're oscillating backwards and forwards by just a little bit. So they're near circular, but not exactly circular. Now, what we're going to be able to do with this is we're actually going to be able to look at this in phase space. So to get an idea of that, let's represent the orbit, let's break the orbit down into different components. So here we have the exactly circular orbit in black, which would correspond to the red one. And the blue one is moving along an orbit that's very close to this, but not exactly. So you can represent it as moving along this orbit and then going around and round what's called a guiding center. This is epicycles, if you guys remember epicycles. So you've got a little epicycle here. The green one has more of an oscillation in and out as it goes around. So it's doing this as it goes around. So this is how we would describe these orbits in terms of epicycles. Once you've gone from that, you can actually start moving into phase space. And I want to show you these phase space projections because this is the sort of data that Gaia can actually plot for us. So we can actually plot where a star is as it moves back and forth here, and we can plot it moving in and out with the Gaia data. In the blue, the orange, like a perfectly circular orbit here, would have 0 radial velocity and it would always remain at the same radius. The blue one, on the other hand, as you can see here, is going in and out in radius. And that means it's actually going, let's see, positive. So if its velocity is positive, it must be increasing in radius. So it's going around this way. So it's going round and round this. That's equivalent to this little motion as it goes around the galaxy. And the same with the green. You're going round and round as you go around the galaxy. So you can relate this directly to those actions. You can also plot the same motion vertically, z versus vz. So if this is the RZ projection now, you can see that the blue orbit is going higher in z than the orange orbit, and so you get a larger excursion in z and vz. So you can relate these projections to actions and angles. Action roughly corresponds to the area enclosed in each of these circles, and the angle roughly corresponds to the phase you are along each of these circles. So you can think of these near circular orbits as going round and round in the galaxy, in and out in the galaxy, and up and down. And roughly, there's an action that corresponds to each of those. The one that corresponds to going round and round is basically your z component of angular momentum. Okay? So this is how you can think about action variables, or how we describe orbits in the galaxy. So now, instead of describing millions of stars along each orbit, you can just say, OK, I have an orbit that's populated with stars at every phase. So it's a simpler description. OK. And the other thing you can do here is plotting it. You can plot the nature of the orbits. Instead of always plotting all the phase coordinates, you can now summarize them in terms of what actions they are. So the circular orbit has, in pink, we don't have the pink one. The orange orbit is circular in the plane. It has 0 radial action, but it goes up and down perpendicular to the plane. So it has some z action. Yes? So it's a way of summarizing orbit. And I've found that missing slide. Here it is. So now we know about orbits. We can actually construct equilibria. We go from the positions and velocities of stars in different populations. If we know the mass distribution, we can calculate their orbits. So we can translate this distribution into this distribution subject to knowledge of a mass distribution. So if you look at this here, this is what Gaia is going to measure for us to describe the galaxy, and we can measure about this part of the galaxy here. Gaia will be able to measure about this part of the galaxy. We'll have this description. We'll have to make some assumptions about the mass distribution and test them, and then we'll have this beautiful equilibrium distribution function of orbits. And of course, this mass distribution, learning about this mass distribution, that gets us back to near-field cosmology, and understanding the orbit distribution for the different stellar populations. So if we add in abundance measurements as well, we get back to these questions of galaxy formation and early universe. Okay? And this is all because of Gaia. Well, and other, a huge part of the dynamical part is because of Gaia. Okay, so that's equilibrium. And this is the first, 3 chapters of Benny and Tremaine. And then we get on to the next chapter, which will be about interactions. Because, of course, in our hierarchically forming universe, galaxies don't exist in isolation. So if we look at what happens in a simulation, this is just low redshift end of the latte simulation from the FIRE collaboration of a Milky Way scale galaxy forming. And you can see this is towards the end of the simulation. It's not the most exciting time in the simulation, but nevertheless, you can see in simulations, and we observe this too, a typical galaxy like our Milky Way may be fairly quiet, but it's surrounded by lots of objects that you can see, dwarf galaxies that are interacting with it. And it's also surrounded by a lot of things that you can't see, which could be dark matter subhalos, and also the dark matter of the galaxy itself, right? So we see evidence of this. This is a beautiful image from over a decade ago now, from the first decade of Sloan data, which is showing you that indeed if we look out around our galaxy, this is looking beyond the disk of the Milky Way, at very distant stars in our halo. And the key point here is simply that this is not smooth. You can see beautiful streams of stars from destroyed satellites. So we have some, beautiful simulations that show us our expectation for hierarchical structure formation, and it's been confirmed in spectacular ways, in many ways, but particularly around the Milky Way, with the discovery of dead dwarfs or remnants of dead dwarfs around them, just from star counts. If you run another sort of simulation, this is one run by Shervin Laporte and visualized by a Columbia undergraduate, where Shervin just took a disk galaxy and threw a satellite at it. It was a satellite that was designed to be rather like our own Sagittarius dwarf galaxy. And you can see these wonderful interactions that are happening between this satellite and the dwarf galaxy. So I'm going to play that one more time. Whoops, I went the wrong way. I'm going to play that one more time. And especially when you see the satellite come around for the second time, you should actually see the disk of this galaxy wobbling up and down in reaction to the satellite. So we've seen evidence for both in simulations and in observations for satellite galaxies being torn apart by the Milky Way. I'll show you later in the talk evidence for the impact of the satellite itself on the Milky Way. And the other thing that I mentioned, of course, is that this is surrounded by a large dark matter halo. So when you see a simulation like this, or indeed the fire simulations, where you're looking at the light matter, you should actually remind yourself that that's on this scale. This is a visualization of what might be happening in a simulation in the dark matter halo. So the galaxy itself on this scale would sit here. And what you're seeing is overdensities and underdensities in the dark matter halo of a simulation of a satellite disk interaction. So the dark matter halo itself is not just sitting there, right? It is also reacting to the satellite. And then the disk is reacting to the halo. The disk is reacting to the satellite. The disk is reacting to itself. The halo is reacting to the disk. In other words, gravity, everything's interacting with everything else. And once you start getting to the level of data that you see in the Gaia satellite, the theme is going to be, you're going to be able to see those interactions ongoing. So this is a beautiful plot that Shervin put together for one of our papers, where he was just looking at the torque on the disk in his simulation as a function of time. And the black is, he isolated the Milky Way halo, the dark matter halo. And this is the end of the simulation, and here's the beginning. So the satellite is falling in. It's getting close. Its orbit is decaying, and it's getting closer and closer to the galaxy. So early on in the simulation, the dominant torque on the disk is not from the satellite at all. It's from the dark matter halo, because the dark matter halo has been distorted by the satellite, and that distortion is being fed down to the disk. So you cannot ignore this distortion. If you're going to model the satellite, you have to model the distortion of the dark matter halo. This is something we've known about for 20 years or so, or more. But nevertheless, I think it's worth reminding ourselves, and it's important to remember that when we start interpreting the Gaia data. OK. So galactic dynamics, interactions, it's gravity, 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 everything's interacting with everything else. So we can, the sort of effects that we expect from hierarchical structure formation, dynamical shocking and heating, wakes in the dark matter halo that are also contributing to this evolution, the excitation of bars and spirals, which I didn't mention, but these can also drive evolution of the disk via beautiful resonance structures. And another thing I didn't mention is all of the things that get excited can phase mix away, and we may be able to see signatures of phase mixing. So what I want to do now is turn to Gaia and actually see what Gaia has shown for us in the last year and a half since the second Gaia data release. And I'm going to go through these slides fairly quickly just to give you a flavor, and then I'm going to zoom in and just concentrate on one particular aspect. But Gaia has shown us another view of hierarchical structure formation. Darn it. Gaia has shown us another view of hierarchical structure formation. Remember, the Sloan Digital Sky Survey and also the 2-micron All-Sky Survey showed us beautiful streams of stars wrapped around our galaxy. those will correspond to fairly recent events of satellites falling in, precisely because we can see them in density. The beauty of what Gaia has shown us is Gaia has been able to take this view of the halo and probe further back in time to the inner part of our galaxy. We'd always thought of the inner part of the stellar halo of the Milky Way as fairly smooth and smoothly distributed. But when you look in the Gaia data set, you can begin to break even that part up. You can't see it as individual streams, but here, for example, here's a beautiful color magnitude diagram. And there's several groups have been looking at this, but I'm just doing a summary from Karma Gaia. Here's a color magnitude diagram from Gaia. And what Karma did was she separated out the thick disk and the thick disk from the halo by just doing a simple cut in kinematic space. And what you can see in the halo, if you look at the color magnitude diagram, you actually see two beautiful main sequences here. And the redder of which looks rather like the thick disk, although it's a little bit hard to tell here, but I'll just tell you that the red sequence here looks rather like the thick disk, and this separate sequence looks like something not like the thick disk. If you plot these two sequences in kinematics, so this is 2 dimensions of kinematics in the disk plane, and this is the radial and vertical dimensions contained. And so in the gray is the locus of where we expect disk stars to lie, and in the blue is the blue halo sequence, and the red is the red halo sequence. And the key point here is these two sequences have very different kinematics. What we actually think is this red sequence corresponds to disk stars that were born in the disk and have got kicked up. And they've got kicked up by the satellite that is now forming this blue sequence, an ancient satellite that came in, and it's now mixed in the inner halo of the Milky Way, and it's forming this blue sequence here. So actually, the blue sequence kicked up the red sequence when it was still one satellite. That's the idea. And we can see this in chemistry as well, and we can see this in the ages. So this is a view of not the more recent accretion events that we still see streams from the outer halo. This is a significant event that happened maybe 6 to 8 gigayears ago in the history of the galaxy. And we're able to, Gaia is able to piece together the history of our galaxy by making these sorts of detailed maps in several dimensions. If you want to look up in the literature, there are various names for this. One is the Gaia sausage. We think that's equivalent to Gaia enceladus, which another group came up with this name. And then there's also the sequoia, which I think is a different event. But we're piecing together the ancient history of our galaxy doing this. OK, so hierarchical structure formation. This is another beautiful confirmation that we think it happened. We've got more details on it now. The second thing is we're starting to get more direct evidence. And I know this is something that Joe Bovey and his group have been studying and are studying. We're getting more evidence in dark matter that the galaxy is hierarchical and structure formation is hierarchical in dark matter as well. Here's a very exciting result that came out very quickly after the second data release from Adrian Price-Whalen and Anna Bernatza. And what you're showing here is actually one of the streams that was visualized in the Gaia, in the in the SDSS data. This, no, it's not SDSS, it's GD1. Sorry, this is the GD1 tidal stream. And this is from the pan-stars photometry of the GD1 tidal stream, which is put together with the Gaia proper motion. So this is one of those streams that was discovered by the older star count data that's orbiting in the outer galaxy of the Milky Way. And what Adrian and Anna did was they used the Gaia proper motions to get rid of the pesky background stars so that you end up just seeing the stream stars. So this is in degrees along the stream, and this has actually been blown up. This is 10 degrees. Oh, no, it's actually equal. So this is 10 degrees perpendicular to the stream. And this is the stream itself in those coordinates. And what you're supposed to see here, which you can see pretty well without squinting too much, is that you actually see the stream looks like it's bifurcated. If you look at the color magnitude of these points and the color magnitude diagram of these points, they look like they have the same stellar populations, and they have very similar populations. So we proper motions. So we actually think this is indeed part of this stream, but you definitely see a bifurcation here. So this was really fun. It was the day, maybe 2 days after the data release, that Anna and Adrian made this plot, and we were in a Gaia meeting at the time. So they showed me this plot. It didn't look quite this nice because they hadn't got so much background subtracted at that point. And then I, of course, being very self-centered, said, oh, it looks just like a paper of mine that I wrote 8 years ago. And so I pulled up a plot from a paper where we've run a bunch of simulations of streams interacting with dark matter halos. And the point here is you see a bifurcation here. I'm not saying this to say, well, I am saying this to say that I'm brilliant, but I'm not. The primary purpose here is to say that this is something that occurs naturally. It's just a gravitational interaction that you fully expect. Indeed, in this paper, we didn't concentrate on this feature at all. We rather concentrated on the gaps because they were more frequent. But it was thrilling to have seen this in the simulations and noted it and thought, well, maybe we should work on it one day and then just have it appear in the data years later. It's really fun to have that happen. Yes?
Is gap also present in the GD1 stream?
I think that you should ask Joe Bovey that question and his group, because they would be able to answer that very carefully. I think we believe some of these gaps are real. The fun thing here was this bifurcation, in the sense that that hadn't been seen before, right? But absolutely, there's a lot of work following on from that by Anna and by Adrian and by people in the room looking at these things. So this is really fun. We've seen hierarchy in stars, and now we're getting the first hints of hierarchy in the dark matter.
What causes these bifurcations? Sorry, I didn't follow.
Oh, right, the bifurcation. OK, so Anna has a beautiful second paper, but essentially what this is you have a stream of stars going like this. Here's a stream of stars. Here's a very straight stream of stars. Dark matter halo comes by it, and it perturbs. Yes, sorry. Yes, so a dark matter halo comes by, and it pulls out part of the stream. And over time, what that means is that it actually sort of gets twisted up, but when it's seen in projection, you can actually see a bifurcation. So Anna has a beautiful paper on this. It's dark matter substructure. OK, so that's what I meant. Thank you for saying that. I didn't realize I hadn't actually said it explicitly. It's the dark matter substructure. OK. The other thing that we are hoping we're getting to see, so this is tremendously exciting, is actually pointing towards a way of perhaps seeing the disturbance in the dark matter halo to its own satellites, due to its own satellites. So that the halo wake, in other words. So if we now zoom in on the orphan stream, this is another part of that SDSS slide that I showed you. This is the Sagittarius dwarf galaxy stream. This is the orphan stream. We can actually look at Gaia proper motions of RL Lyrae stars in the orphan stream. And this is a paper by Sergei Kopasov and some interpretation by Dennis Urkel. And again, we're looking along the orphan stream in degrees, and this is perpendicular to the stream. In this case, this axis has been blown up. So you can see where the RL Lyrae are falling. This is the stream track. And the key point is that the proper motions of these RL Lyrae do not lie along the stream. And this has been seen for the orphan stream. It's also been seen for streams in the dark energy survey, that in many cases, but not all cases, the proper motions from Gaia are not lying along the stream track. Now, you might expect a small difference in the actual motion of the stars versus the stream, but having this big a difference does not make intuitive sense. And the interpretation, the qualitative interpretation so far, is that this is because the stream is not just being accelerated towards the center of the galaxy, it's being accelerated by distortions in the dark matter halo that are not taken into account in the simple model. And also distorted by accelerations with satellites as well. But the reason I'm not pointing this only to satellites is because this is a very large-scale distortion in the proper motions and not just a small-scale distortion. So I think it's a reasonable interpretation, but it hasn't been quantitatively proved at this point. OK. Another example for the halo wake. This one comes from, these are the proper motions, sorry. These are the proper motions on the DES stream. So each of these is a stream, and some of them you can see the proper motions are aligned with the streams, and some of them just aren't aligned with the streams. OK. So I'm looking at the time. I'm going to skip over the next slide in order to make sure that we have time to get to a couple of other things I wanted to talk about. So there's another halo wake example. What I wanted to get onto now is to dive into the disk. So I'm going to show you a couple of different views of the disk and then concentrate on one example in particular. So we think of our disk of stars as rather like this, stars going around in a circle in a disk. That's why it's called a disk. So I had them going the wrong way. And there are some spiral structures. One of the fun things that was hinted at in data before the Gaia satellite came out is not only are the stars going round and round, they're going up and down as well. I already told you that. But what I certainly had not thought about a lot is actually the whole disk is wobbling up and down slightly. And I don't just mean a warp motion. I actually mean ripples in the disk. So this is beautifully shown in the Gaia data. We could see it in, if we looked really carefully in RAVE and SDSS and LaMost, we actually saw it pre-Gaia. But it's beautifully shown in the Gaia data. What we're plotting here, if you look, let's look at the red and the blue. Forget about the green for now. We're plotting the radius in terms of actually the guiding radius of the star. So that's the parent orbit of each of these stars. And what you're plotting, let's look at just the blue. The blue is the up and down motion of those stars. And what you can see is that the up and down motion of these stars on average is not zero. So if the disk stars on average were just orbiting and at random, going up and down at random, you would expect the blue line to sit at zero. But instead, you can see that there are systematic variations on scales of about a kpc or so. And you also see this in terms of the disk as a whole. It's going in and out as well with variations on order a kpc or so, and amplitudes of a few kilometers per second, 5 to 10 kilometers per second. So the reason this hasn't been detected before is because we just haven't had the quality of the data in the distances to be able to separate this out into these rings and in the velocities in order to be able to see the amplitude as well. So we can see this in terms of velocities, now that we've got 6 dimensions. The original Gaia DR2 paper, this came out on April 26th from the Gaia team. So if you look in x versus y, the sun would be about here. You can actually see in radial velocity systematic variations, and also in vertical velocity. Oh, sorry, it's this one. Vertical velocity, you can see systematic variations. This part of the disk is going up, and this part of the disk is going down, right? So the whole disk, in a mean sense, has these perturbations of scale about a kpc and 10 kilometers per second going on. And then another example of the beauty of the data set. This one I'm going to skip over, but I want to show it to you so you can go back and look at it at your leisure. Another example of disk response is that you can see resonance structure in the disk, in the sense of what we're plotting here is angular momentum and radial action. So in other words, this is orbit structure. This is orbital action, 2 orbital action quantities. The only point I want you to take away from this is not smooth, right? If we wrote down a function, if we want to write down a phase space distribution function in actions, f of j, we usually assume it's smooth. This is way, way far from smooth, right? I say way, way far. These fluctuations are small, so it's not smooth is the key point. So I'm not going to talk more about that. I'm going to go on and instead talk about phase mixing, because I think this is maybe the most fun result that's come, well, it's hard to say. This is one of my favorite results that have come out of Gaia. And I didn't point this out before, but what I'm trying to show you here each time is what sort of volume of the galaxy we're looking at. So what I'm going to show you now is taken from stars that are within 1 to 2 kpc of the sun. This is the region where Gaia errors are the smallest, so you're able to map the phase space most accurately. And this was a result that came out the day after Gaia by Teresa Antoja and Amina Helmi and their group. So this is the day after Gaia DR2. We all woke up in the morning to this paper. It's plotting position, z, relative to the galactic disk, and vz relative to the galactic disk, just for stars within 1 or 2 kpc of the sun. And it's color-coded by the mean azimuthal velocity in each of those boxes. And I hope I don't have to point this out, but I will for fun. You see a beautiful spiral in this plot, a really beautiful spiral. And this, we believe, is a signature of phase mixing from a past interaction. So in other words, if we think about this for a second, our expectation here is that in this plane, remember, a ring in this plane corresponds to a single orbit. This is the same as the action plots I showed you earlier. So this is an orbit, would correspond to a near circular orbit, just oscillating slightly up and down in the disk as it goes around. And this is a circular orbit oscillating up and down a lot. So what you're seeing here is the fact you see a spiral. This is telling you that those orbits are not completely mixed. There's some certain phases of certain orbits are picked out. And they're not picked out at random. You're seeing a beautiful coherent structure. So what I wanted to dive into here, make sure I had time to dive into, is to just describe phase mixing a little more, because this is a lot of fun. It's simple physics and it's a lot of fun. So this is what I was reminding you of. This is a plot I showed you earlier. These are what single orbits would look like. We'd expect this, therefore, just to be a filled circle of stars at random phases, but it's not. We're seeing stars at specific phases at specific orbits. So I've got this poor person's cartoon of what's going on. So here we are, we're sitting at the sun. It's going at a near circular orbit around the galaxy, and we're looking at this volume of stars. In fact, you actually take a set of stars here with different angular momenta, but they're observed in the same volume. They just have different angular momenta. You integrate them backwards one orbit ago. The red stars are the stars that have the same angular momenta as the sun. The yellow have lower angular momenta, an orbit typically closer to the galaxy. And the blue have higher angular momenta, and they orbit further out. If we look at this 2 orbits ago, you can actually see that they tend to split further apart. So the stars that we now see within this blob are a combination of stars that were once spread around the galaxy. And they were spread systematically in accordance to the angular momenta that they have. So what we did here is we took a set of stars that initially have random z positions and random vz positions. And we just offset them slightly. In other words, we pretended they'd been kicked slightly in their orbits. So you can see this is where they would be if they were centered on 0, 0. And this is as if they've been kicked slightly in their orbits. If you let that go forward, and we do that as if it's 2 orbits ago, and then you let it go forward, what you can see is the blue, red, and yellow stars that were originally randomly distributed. Because of that kick, they wind up and they form a beautiful spiral, right? So the idea is something has come along to the galaxy and kicked it, and what we see today in the phase space distribution function is a spiral. Right. So having got that intuition, we can actually look at this and say, okay, I see this spiral in this data, but actually, if something came along and kicked the yellow, red, and blue stars, 2 orbits ago, they were all at different places in the galaxy. So maybe they got different kicks. So with that in mind, Shervin and I made this movie, and this is real Gaia data. So actually, I didn't make the movie. Shervin made the movie. This is real Gaia data. And what we did is we split it, the same 2 kpc region. We split it according to angular momenta. So you're going to see a movie going through where we're plotting z versus vz over density. And we're going to go through in bins of angular momenta. It's as if you're sliding in and out of the galaxy, actually from the out to the in. And what you can actually see when you do this is you start by seeing a spiral that goes up and then down. And then by the end, you see a spiral that's going down and then up. So this is real data. I'm going to play it one more time because I love this movie. And you can see the spiral is gradually changing as you look at different angular momenta. So let me go back again. We'll play it one more. Oh dear, sorry about that. Play it one more time. So this is a spiral in the Gaia data at high angular momenta, and as you move to lower angular momenta, the phase of the spiral is changing. So what we actually think we're seeing is interactions that may have occurred at the same time, but they have a different sense in different parts of the disk. So the fact that that the disk actually mixes because you have differential rotation is a beautiful way of us being able to look at local data, and we can actually look at the history of the disk in different parts by playing this trick by looking at it in different angular momentum slices. So this is tremendously exciting. You can imagine there's been about 10 papers on the Gaia spiral. In fact, I had this great experience where I was sitting at a conference. There was a whole day of talks on the Gaia spiral, and everybody in the audience was totally sick of it by the end of that time, but except for a few of us who are actually working on it. But I typically have had that experience when we've instead been talking about, I don't know, the profile of dark matter halos in cosmological simulations. Have you ever been? I have. Like my generation, we used to sit through days and days and days of that, which was very important, but it was mind-numbing. So now I've had the experience of from the other side, of being someone who's actually working on the problem and boring the rest of the audience. It's great. So you got the 10-minute boring. I hope you found this part. It's exciting for at least 10 minutes, right? Okay, so I have to show you in Sherwin simulations, of course, the day after the morning that we saw the Gaia spiral come out from Teresa Antoja and Amina Helmi and collaborators, that morning, we'd already run these simulations. So I got Sherwin to actually look in his simulations and see what he saw. And actually, we'd done this part at least before Gaia. So this is showing you actually, this is timed from the last impact of simulation of Sagittarius in his simulation. And what you're looking at is the vertical velocity looking down on the disk out to scales of 20 kpc. You can actually see Sagittarius going through the disk here, which is rather fun. And you can see that the disk in the simulation is wobbling up and down in qualitatively a similar manner to what we actually see in our own disk. But the fun thing that we then did was, OK, let's see if we can see a phase spiral forming. And indeed, in these simulations, you can see a phase spiral forming due to this impact of Sagittarius on the disk, which is really fun. And you notice that this data does not look nearly as nice as the real data. Why? Because we now can see the galaxy in higher resolution than we can simulate it, which is really thrilling, right? Usually it's the other way around, right? OK, so welcome to the Milky Way. Let's see. So what have we found? We found that we started from wanting to make a phase-space distribution and function in orbits. This beautiful distribution function is supposed to be smooth. And within that smooth distribution function, it should be randomly sampled. We've actually found that orbits in the galaxy and the galactic halo are non-randomly sampled. This distribution function is made in a time-independent potential, and yet we found evidence that the Milky Way on even large scales is time-dependent. It represents an equilibrium function, and yet we find ripples in the disk going up and down at 10 kilometers per second. It's supposed to be a smooth function. We see that it's jagged, and it's supposed to have no phase dependence, and we see phase dependence. So this is somewhat confusing. It's not that it's not expected, it's totally expected. So, but it's not something that we had tried to deal with pre-Gaia in order to interpret our data sets. So here I've put just two of our simulations together for a take-home point here. Here's the Milky Way being perturbed by a satellite galaxy. Whenever you see a simulation like that, you should remember this is probably what's going on in the dark matter halo, which will be, the effect will be proportional to the mass of the satellite, of course. So this is a beautiful paper by Gus Bean, where he actually looked in the fire simulations to ask, OK, well, so suppose we calculate actions in the fire simulations at different places along a single orbit. What would we find? And this is what he actually found, is that the actions that you calculate at different phases differ by more than tens of % as you go along. So what this actually means is if we make beautiful action plots, which we can now do with Gaia Data, exactly how we interpret them is a little confusing because those actions themselves are oscillating on an orbital period because of the fact that the disk, for instance, is not in equilibrium, but actually oscillating up and down slightly. So this is the conclusion of my talk. But I don't want to leave it as if we really don't know what we're doing. It's exciting. It's an exciting time to be, in fact, it's a thrilling, magnificent time to be a galactic dynamicist, precisely because we're going to be working from all of the wonderful work that we have developed, and much of it is encapsulated in Binny and Tremaine's wonderful book, with all the equilibrium modeling that we had developed to interpret Gaia. But the data set is so beautiful that in order to get to an accurate interpretation, we have to go beyond the equilibrium modeling. We'll be able to learn a lot with equilibrium models, but at least at the 10% level, it's out of equilibrium. And if we want to measure things to better than 10%, we're going to have to model the out of equilibrium part of this. And so I think there's a lot of work to be done. And my solution to this problem, I have two solutions. The first one is to leave it till the next generation. But no, that's not. That was a bit of facetious. We are running an applied galactic dynamics school at the Center for Computational Astrophysics next summer. And it's called Applied Galactic Dynamics because we're going to take galactic dynamics and think about how to make a direct connection to the observational data set. Currently, the theorists are talking one language and the observers are talking and finding another language, and we really need to connect those two things. So please come as a student or send your students. This should be a lot of fun. It's going to be 7 weeks long. I think, and I'd also say this is as much for the mentors as the students to try and understand how to deal with the data set. And lastly, I didn't want to leave you thinking that I'm just sitting there going, ah! So these are the sorts of things that my group is working on, or people I'm working with are working on. These beautiful phase mixing structures I showed you, you can imagine they contain an immense amount of information. So I think a large portion of thinking is about how to interpret those phase spirals. And hopefully we'll get more phase spirals as Gaia's data set extends. A second thing is, OK, if we're going to throw out actions as being conserved, then we want to find another conserved quantity to understand that evolution in itself. And the obvious thing to turn to is stellar abundances. And so I'm working on a project using abundances as our key dynamical tags to actually understand how the actions have evolved, given the abundance patterns we see in the Milky Way. And then the last major area that we're thinking about is precisely this, how do you connect data, theory, and simulations in a dynamical way, a dynamically informed way, in order to make the most of this data. So, right, that's it. Gaia is great. The results are amazing, and we're having a lot of fun. Thank you.
Thank you so much, Kathryn, for a wonderful talk.
Is there any sense now the process of the event that triggered the formation of the galactic bar?
Oh, right. I think that's a great question. The simulations, Shervin simulations naturally make this with Sagittarius, but I don't think that means that's the answer. You can also, the LMC could also create it as well. So I think that the jury's out on that. The fun thing is there have been papers on this phase spiral which are suggesting you can get a spiral set off from the actual instability in the disk, the bar buckling itself, because it's going up and down. So that can also set off spirals. So if we can separate the spirals that are formed by Sagittarius directly from those that create the bar buckling, we might be able to figure out that question about formation. We may actually be able to see signatures of the bar formation in spirals as well. But we have to be able to separate them.
And in understanding these departures from axis symmetry,
yes.
Is there a sense of how much the dark matter is playing a role versus the stars.
Right, so in the simulations we've been able to separate that. And as I showed you early on, it is the dark matter halo that's more important than Sagittarius itself. I think that my intuition would be in the outer halo, so I'm talking 40, 50 kpc, the LMC is a major player. I also think this dark matter halo wake will be almost equal to the LMC because it's the LMC that's creating it, so it's proportional. In the inner galaxy, I think you're more dominated by the stars themselves and the bar. That's going to be a major player. The spiral arms, Sagittarius directly, and also the galaxy itself going up and down. So I think different portions of the Milky Way, you're going to get different answers to that question.
So if you unwind that spiral,
Yes.
Does the time does the time of the kick then correspond to the time Sagittarius comes through?
Yes. So people have, the very first paper did try and do that. And so roughly, yes. But I think that the jury's out as to whether whether the simplest interpretation is the correct one. So for instance, if you run a simulation, Larry Widrow has done this. You can run a simulation, actually the first author is Darling and Widrow. You can run a simulation of a disk in a dark matter halo where you have no self-gravity in the disk and you just kick it. And indeed you would see the spiral and it just, you can see it wind up and you can go backwards. If you add the self-gravity of the disk, well guess what? The disk is going up and down now too. So you can actually fuzz out that spiral or even set off new spirals because the disk itself is self-interacting. So I think I'm not convinced that we know the correct interpretation at this point, although I'm tempted to be able to say that you can simply rewind them. Yes, that would be great.
The time when Sagittarius comes through.
It does, yes, I mean roughly. So yes, it fits order of magnitude, yes.
Order of magnitude is a long time.
Okay, factor of 2, yes, to factor of 2 fits.
Other questions?
Time for cookies.
Yeah. Please.
Is it me or something?
No. I'm just curious about these little wiggles and clumps in the action space that you're talking about.
Yes.
So are those corresponding to the ones you were showing the simulations later on?
Right, so there's, let's see. Right, so these action space, this is the plot which was in action space, and these are the wiggles here. And these, one way of explaining these is that if you look in this space, you expect resonance structure to lie basically along sort of these vertical lines going up, and you can actually overplot where you would expect the resonances with the bar and with the spiral arms. So one interpretation of these is these have to do with resonances with the bar and the spiral arms, and less with the this vertical oscillation. So that would be another talk to talk about that part.
But that's only some of the structures, not all the structures.
Yes, it's true. Like, yes, it's complicated, as you're pointing out, right? So I think that's part of what we need to do is understand how to disentangle things cleanly from each other, because there's lots of structures going on. Some are resonances, and some are due to perturbations that are phase mixing. So for some, self-gravity is important. Oh, and some could also be disrupted clusters as well.
When you talk about using abundances as another axis, that's only applicable with the disrupted clusters?
Whether it's bound? Sorry.
No, abundances.
Oh, abundances. Oh, no, absolutely. No, yes, very good. Yes, absolutely.
But that's only for certain circumstances that's useful.
Well, you can, one of the games we've played, but we haven't come to a firm conclusion yet, is to actually, exactly your suggestion, look in this space and find clusters, and then look and see if the abundance patterns are similar or different in the different clusters. So absolutely, we're using abundances as well. The other thing, sorry, let's say you mentioned clusters. So one if it was, if one of these lumps was a disrupted cluster, there would be monoabundance. But the other thing you can see in this plane, and Joe Bovey has written a paper on this, is you can actually see that some of these streaks are metal rich and some are metal poor. And so you're actually seeing motion, global motion in the disk. So that's also interesting, right? Yes, yes. I think the problems are complex. I'm hopeful that we will be able to distinguish them because we have these high dimensional spaces. It's a question of coming up with unique signatures for each of the processes.
So I was wondering, in different parts of the disk, perhaps say regions with higher star formation rate, would it be possible to, would you expect the spiral structure from phase mixing to be more intense in regions, say, where there have been a large number of supernovae, and whether that could be used to, say, map out these kind of high.
So you're sort of thinking the impact might have driven some supernova, and then that in turn, if the impact might have driven some supernova, and that in turn would highlight the spiral.
Oh, I guess I'm wondering if there's a region that has a very pronounced spiral effect. If the dynamics on the nearby region as a consequence of, say, some number of supernova picks could impact on the dynamics.
Ha, that's interesting. I haven't actually thought about that at all. I'm all about throwing dwarfs in rather than the supernova going off. No, I hadn't thought about that at all. That's an interesting question. So I don't have a good answer.
Well, I'm curious, when the final data releases out, what are the qualitative and new things that you're going to do that you can't do now?
Yeah, so I think there's going to be a big leap with the next data release because the mission will be twice as long. So the error bars are going to be half. So there's two different things really going on is, there's regions where the error bars of the galaxy, the reason people are looking just a few kpc is because the error bars become too big, right? So basically the horizon of a few kpc is going to end up more like 10 kpc.
So you know, sample most of the galaxy.
Yeah, exactly.
So global effects are going to be much better constrained than...
Exactly. So we should be able to look at this phase spiral as a function of location in the galaxy, as well as we've already done that split on angular momentum, which is sort of a cheat.
That's
But
going to be important for distinguishing different types of structures.
I think so. I think so. The other thing is that Gaia's been so successful, they've already extended the mission, which means, if we wait 10 years, then it's going to be 4 times better, etc. Yes, it's good news. Yes. Okay.
Okay, if there's nothing further, let's thank Kathryn again.
Okay.